Welcome, physiotherapy students, to this exam prep bootcamp explainer. Today, we're locking down the absolute foundational physics you need for electrotherapy. I want you to get into a very specific mindset for this session. Imagine you are the conductor. That stimulator machine sitting right next to the treatment bed, that's your source of energy. And your patient's body, that's the circuit. Everything we're going to cover today is all about bridging the gap between your physics textbook and delivering safe, effective treatment to that patient. Let's get into it. All right, here's our official exam syllabus for today. We're going to quickly hit 5 key areas. Number 1, the spark, that's current and EMF. Number 2, the obstacle, which is resistance. 3 is circuit safety. 4, the golden rule of Ohm's law. And finally, number 5, clinical applications. Okay, let's dive into this. Section 1, the spark, current and EMF. This is where the magic of electrotherapy really begins. So, current. It's basically just the flow of charge, specifically electrons, moving through a conductor. In physics, we measure this in amperes, or amps, which is literally just 1 coulomb of charge passing a point every single second. But, for this flow to actually happen, you absolutely need 3 specific things. First, a source of energy, like a battery or the generator in your clinic. Second, a conducting path. And in our world, that path is human tissue. And finally, you need a potential difference to actually push it all along. Now that push brings us to EMF, or electromotive force. Guys, flag this as a high-yield exam tip. EMF is the energy supplied per unit charge by the source itself, and we measure it in volts. Think about it in terms of your everyday physiotherapy equipment. Your stimulator machines are literally built to generate this EMF. It's the vital energy required to produce those therapeutic muscle contractions in your patients. Okay, let's clear up a classic exam trick right now. Professors love to test if you know the difference between these two. EMF and current are definitely not the same thing. EMF is the driving force, right? It's the pressure causing the movement. Current is the actual flow of the charge itself. You can absolutely have EMF without current, like imagine a machine plugged into the wall but turned off. But there is absolutely no way you can have current without EMF pushing it. Keep those two totally separate in your mind. Moving right along to Section 2, the obstacle, or understanding resistance. Because as we know, energy doesn't just flow freely, it always faces a little pushback. So, what is resistance? It's simply the opposition to the flow of current. It's the physical pushback against that electrical flow you're trying to send right into the tissue. We measure this in ohms. Honestly, the easiest way to think about it, if EMF is your foot slamming on the gas pedal, resistance is the brake. Now, for your exam, you absolutely have to memorize the 4 main variables that dictate exactly how strong this pushback will be. Let's just rhythmically punch through them. First up, length. A longer path means increased resistance. Second, cross-section. A wider or thicker path actually decreases resistance because it gives the current more room to flow. Third is material. Different substances just conduct differently, right? Like highly conductive copper versus really resistive nichrome. And fourth, temperature. Lock these 4 variables into your brain right now. All right, Section 3, circuit safety. Series and parallel. Now, what's really interesting here is how these physical obstacles translate directly into keeping your clinical devices safe. Whenever we combine resistors, we can do it in a series or in parallel. In a series circuit, you literally just add the resistance up straight across the board. The current stays exactly the same, but the voltage divides. We use this when we intentionally want a high-resistance circuit. But over on the parallel side, take a look at that fraction formula. In parallel, the voltage stays the same, but the current divides across the different paths. So why does this actually matter to us as physios? Well, because parallel circuits are specifically utilized inside your physiotherapy machines. By dividing the current, this parallel design fundamentally protects the delicate internal circuitry from burning out. Pretty brilliant, right? That brings us to Section 4, the golden rule, Ohm's law. Listen up because this is the absolute most critical formula for both your clinical practice and your upcoming exam. V equals I times R, Ohm's law. It states that the current flowing through a conductor is directly proportional to the potential difference across it, provided the temperature remains constant. The clinical link here is absolutely massive. This single formula literally dictates how you adjust the intensity dials on your machines during galvanic and ferrotic stimulations. Every single time you turn that knob up, you are manipulating this exact equation in real time. So the crucial point is knowing exactly how to calculate this on the fly. Let's walk through a super simple calculation step by step to really lock this in. Step 1, your exam question gives you a voltage of 12 volts. Step 2, it gives you a resistance of 6 ohms. Step 3, just apply the formula. If V equals I times R, then to find current, which is I, you simply divide voltage by resistance. 12 divided by 6 gives you a current of 2 amperes. It's simple, it's direct, and it is pretty much guaranteed to be on your test. Okay, final stretch, Section 5, Clinical App, Beating Resistance. We are taking all of this physics out of the textbook and bringing it directly into the clinic room, right onto the patient's actual skin. Consider this practice scenario for a second. If skin resistance is incredibly high, how much more voltage is needed to maintain the current? I want you to really think about that. Mathematically, if R goes way up, V has to go up just to keep I the same. But clinically speaking, is cranking up the voltage really what you want to do to your patient? And this brilliantly illustrates the difference between purely solving a math equation and actually being a great physiotherapist. If you just spike the voltage to overcome dry, highly resistant skin, you are seriously risking a painful shock or even a burn. Instead, your secret weapon is conductive media. By applying ultrasound gel or saline water to the electrodes, you drastically drop the patient's skin resistance. By lowering that R, you allow the current to flow freely, and you completely avoid needing a dangerous, massive spike in voltage. I want to leave you with a final thought today. Thinking back to Ohm's equation one last time. If voltage equals current times resistance, how does balancing your machine's power with your patient's skin resistance ensure you provide completely safe, effective electrotherapy without causing a shock? You see, physics isn't just about passing this exam. It's the invisible safety net you cast over every single patient you treat. Understand the current, manage the resistance, and you will master the machine. Good luck studying, guys, and I'll see you in the clinic.